Okay, chapter 4 of functional programming in Lean, monads. And in the introduction here, we see some examples of monadic structures in like non-functional programming languages, like for example chained null checks or exception handling, or another one would be, for example, async await, like it's implemented in JavaScript or in Rust. 4.1, one API, many applications. And yeah, I mean, you will find these kind of APIs probably in every programming language. And the difference with some functional languages is that they sort of recognize this common pattern and provide an abstraction for it, and also like a special syntax for it that is general to all monads. Like for example, JavaScript also provides special syntax like async await, but then that only works for that one particular instance of like the promise type and not for everything else. 4.1.1 checking for none, don't repeat yourself. So in this example function here, we're trying to get the first element of a list. Obviously the list might be empty, so we are returning an option here. And as we saw in the previous chapter, there's this sort of question mark indexing syntax that will either return none or some in case there's a first element. But if we want to make a function that returns the first and the third element, then it gets significantly more complicated, because if there is no first element, then obviously we need to return none. But if there is a first element, then we need to check the third element. And if there's no third element, then well, we need to also return none. And if there is a third element, then we return this tuple of the first and the third element. Obviously, the more elements you do this with, the more nesting you need to handle all these conditional cases. And obviously that's a lot of boilerplate, so that's something we want to avoid. I mean, here with 4 elements, it gets basically ridiculous and the code becomes just more and more indented. And yeah, one way to clean this code up would be that if we just create a helper function, and then that takes an option of type alpha, and a next function that then takes an alpha and produces an option of beta. And yeah, the result of the whole function will be then an option of beta. And if we match on the first argument, well, if it's none, we just return none. And if it's some x, then we call the next function on x. And this helper function basically now does the same thing as the question mark dot operator in C# and Kotlin, and I mean also in JavaScript, for example, which is to say that it takes care of propagating the none values. And what we can now do is we can write this first and third function, for example, using this and then helper, and I mean the code becomes a lot cleaner and also doesn't get like more and more indented. Like if you compare the original implementation where we had like 3 indentation levels essentially, now we only have 1 level. 4.1.1.1 infix operators. Yeah, one thing that's special about Lean is that we can make our own operators and can use the infix command for a non-associative, or infix L for left associative, or infix R for right associative operators. And the associativity obviously just means how basically the order of operations works. So if we say plus is left associative, then in this expression it's going to be evaluated like that, so that basically w plus x is evaluated first, and then the result of that is added to y, and then finally the result of that is added to z. Though obviously in case of plus it doesn't really make a difference. You could also declare it as right associative and get the same result. But for exponentiation, for example, obviously it matters, and the convention is to treat an exponentiation expression without parentheses as right associative, so that basically the rightmost sub-expression is going to be evaluated first. And for some operators there is just, well, no good default, or that would like not be confusing, so those are just declared as non-associative, like the smaller than syntax. I mean, with 3 cases, actually, you could, like with 3 arguments, you could make basically the case that it should be saying that y is between x and z. I think in Python, actually, you can even write that. But obviously, if you had a force, then at some point it becomes confusing. And obviously, that's also not what this expression means. So even if you like insert the parentheses here, then like it would evaluate this sub-expression and then give you a Boolean and then compare x to that Boolean. Okay, and now we can declare an infix operator for our and then operation, which I'm guessing this is the priority, and then this is the operator syntax. Okay, yeah, so the number is the precedence, and for example, the plus operator has precedence 65, and times has precedence of 70. And we are now at a lower precedence than plus and times, so it's gonna be evaluated after arithmetic expressions, I guess. Yeah, I think like one of the disadvantages of allowing this in your language is, well, with a large group of operators, it gets very difficult to manage all of the precedences. And also, like, if you don't have the information in your head, like which has what precedence, then, I mean, in the case of arithmetic expression, we all know that the times has higher precedence, so we're gonna have to evaluate this first in our head. But if you have like thousands of operators, then it gets really confusing. I think that, for example, in Haskell, you can also declare your own infix operators, but in many cases you don't have to, because you can just call a normal function like mod. If you put it into backticks, you can like call it as an infix operator. I think that is, for me personally, at least a lot more readable than like making up a special syntax for every little thing. But pretty sure actually that Lean doesn't have this sort of backtick syntax. So obviously in case of the plus operator, it's defined as this sort of hadd function from the hadd type class. But as we see here, we can also just use a regular function that's not part of a type class to define an operator. And yeah, now we can rewrite the function using our weird squiggly arrow operator and make it a little bit shorter, I guess, especially if you have like a lot of cases. 4.1.2 propagating error messages. Yeah, so Lean doesn't have built-in exceptions like Java or Python, but like we will see later, we also don't need that because like exception handling is also just like a special case of a monad. So for example, in the functions above, we're always returning none in case of an error, but sometimes you maybe want to add more information, like which position of lookup failed. And the way you do that in the functional language is to make like an algebraic data type or inductive data type, which either contains an error value or it contains an OK value. So like the result type in Rust, for example. So we have this inductive type except, which takes two types, epsilon for error and alpha for the OK type. And yeah, it's really just like either or kind of thing. Either it contains the error value or it contains the OK value. And obviously you cannot get the OK value out of that type without pattern matching. So basically you're kind of forced to handle both cases. You cannot really forget to check for an error. So we can define a get function that gets an index I from a list XS. And in the error case, we just return a string with a helpful error message. So if we now rewrite our list lookup function that performs two lookups using this except type, then we are sort of back to square one. We have the same issue where we have to indent the code further and further to handle the error cases. And I mean, obviously, the more levels you add, the more ridiculous it will get. And we see again this common pattern, and again we can define our helper function, and then which takes an accept value attempt and a next function that takes the OK data type and produces another accept value with type of the error of the first value and the new type beta as the OK value. And we are pattern matching on the first value, and obviously if the first value is an error, we just return the error, and if it is okay, then, well, again, we call the next function. And yeah, in exactly the same way as before, we can call this and then function and get a more concise definition of this first third function without having to do all the if-else switching for the error cases. And okay, now we're defining two helper functions, basically just to shorten the constructors of except. And we can make the get function even more concise using those two helpers. And obviously in the same way, we could also define our operator again and make it even shorter and scale better to larger functions. 4.1.3 logging. So we can define an is-even function that checks if the remainder of dividing I by 2 is equal to 0. Okay, we define a silly function, sum and find evens, which will sum up a list and also return all the even numbers inside of that list. So if so we're pattern matching on the list. If it's not empty, we call ourselves recursively on the tail of the list, and then we check if the first element is even, and if it is, then we prepend it to the more even result list from the recursive call. Otherwise we just keep it as is, and obviously we add it to the total sum. And the common pattern here is that we are traversing a data structure while on the one side computing some result, and on the other hand we are accumulating some extra information that we also need in addition to the main result. And I mean, one prime example of this is logging. So while we're computing something, we might want to provide some log messages for debugging purposes. And usually, I mean, you would write those to a file, so either a file on disk or like a file descriptor like standard output. But obviously, in a functional programming language, you cannot just do that inside of a pure function. Or another silly example they have here is a function in order sum that will take a binary tree of integers and return a list of the integers encountered as well as the sum. So in the non-trivial case where we have a branch with an integer and the left and the right subtree, we obviously need to call it on both the left and the right subtrees and, well, add our current value to the sum and to the visited lists. And obviously this is all like the same pattern where each step of the computation returns a list of the like site or auxiliary data and the main result, and then we are appending something to the list and also computing something with the primary result. So I guess now we can create an abstraction for this by making a structure with log that takes a type logged and a type alpha and has two fields, which is a list of the type logged and a value of type alpha. And then also for that case, we can abstract the pattern using an and/then function that will first take a result of type with log alpha and beta, and the next function that takes beta and returns a with log of alpha and gamma. And the result of the whole function will be a with log of alpha and gamma. And I mean, this is exactly analogous to the case that we had with the except type, except that it's now called with log. But otherwise the type signature is like the same. So if we pattern match on the result and also pattern match on the result of calling next on the resulting value, then our final value will just be, well, the log value of the next function appended to the original log value, and the value itself will just be replaced by the result of the next function. Again, we can also define our OK function again, which in the case of logging would just be a function that doesn't log anything and just returns its value. And instead of having a fail function like in the except case, in the case of with log, we have a save function that just returns a dummy value but saves the data to the log. So now we can rewrite our earlier functions using this and/then function, and we can see here, so the first thing that we evaluate is going to be this, which if I is even will save I to the log and otherwise just return a unit. And then what we do with that is we essentially pattern match on the unit value and call and/then a second time, this time like using the recursive call, and obviously then we get the sum back and we can add I to the sum and use the OK function that doesn't log anything to create the result. And like literally the analogous thing for the binary tree function where we save the node itself to the log. And again, we can see here that doesn't return anything interesting, so we just have this pattern for the unit type. And in the end, again, we use the OK function that doesn't log anything new, but it's the value. And literally analogous to the earlier cases, we can then create an operator for the and/then function and rewrite it using using the squiggly arrow operator. 4.1.4 numbering tree nodes. And I guess the point of all of these examples is just to show us that the monad pattern just appears over and over again, like to motivate, I guess, the monad type class, which we will see in the next section. So an in-order numbering of a binary tree associates each data point in the tree with the step where it would be visited in an in-order traversal. And okay, we define this a tree inside of this open expression, that we don't have to prefix each constructor with like the bin3 namespace. And in that case, the in-order numbering would be another binary tree where each value is replaced by a tuple with the index and the value again. So obviously the natural way to write a function on trees is to use recursion, but apparently it's tricky to compute this sort of in-order numbering using recursion, because the highest number in the left subtree obviously determines the index of our current node as well as the index of the right subtree, or like the starting index of the right subtree. And in the imperative language, maybe you would use this by you would solve this by using mutable state. So we have here an example in Python where we have a class branch that has left subtree, a value, and the right subtree. And for our number function here, we define a starting index of 0 and then a local function helper of t, which will access this sort of mutable state from the containing function. And obviously now first we will call the function recursively on the left subtree, and this will like mutate the index value here so that by the time it returns, it's now the correct index for our current node. And then we increment it and call it on the right subtree. And I mean, obviously that's a trivial function and appears to work. But obviously in Lean we cannot directly have a mutable variable because it's a pure functional programming language, but we can do a workaround. And I mean, if you think about what we care about from this mutable variable, it's just that well, we want to know the value before we we do the recursive call and the value after the recursive call ends. So basically we can think of a function that takes a mutable variable as well, taking the initial value of the variable and returning a tuple of the final variable and the actual result of the function. And so with that pattern we can sort of copy the Python code in Lean and do a similar thing. So we have our number function which takes a binary tree and returns a binary tree that extends the values with these indexes. And we have our local binding where we need to use letRec because it's a recursive function. We call it helper of n natural number, which is I guess the starting value then. And it's going to be a function from a binary tree of alpha to a tuple, which is a natural number, which will be then the final index, and well, the augmented binary tree. So first we call it on the left subtree, where again we get the next index, which we then increment +1 to call it on the right subtree. And as a result, for our current node, we return the current value, so the next index, like the result of the mutable variable after calling it on the right subtree. And obviously we return a binary tree which contains the numbered left subtree, our current extended data point, and the numbered right, and we just call it with 0 and the tree and throw away the last value of the mutable variable and just return the second value, which is the numbered binary tree. And I mean, literally we see the same pattern again as we saw with the option and the error handling and the logging, where on the one hand we are propagating a value and on the other hand we are like actually computing a result. So if we want to abstract this, again using an and-then function, we need to like have a data type for this sort of quote-unquote mutable state that we have. So we can see here we define state, which is a function that takes a type sigma and a type alpha and returns a type. And honestly, I think it's confusing, but what I think this is saying is, so we have here like a function on the type level, so a type constructor essentially, and the result of that is a function on the value level, so that takes a value of type sigma and then returns a tuple of values of type sigma and alpha. So in this example, our OK function would take a value of type alpha and return a state of sigma and alpha, which will then be a function that takes a value of type sigma and like just passes it along unchanged, but also returning our input of type alpha alongside with it. Yeah, so obviously with mutable variables, the two operations that we're going to need is reading the current value and replacing the current value with a new value. So we define this get function, which takes a state of sigma and sigma, which is of type state sigma and sigma. And the yeah, so state is a type constructor, but the type that it constructs is a function. So if we look in the definition, then the function here will be, well, taking a sigma and returning a tuple of sigma and sigma. So yeah, we take a value s of type sigma and we return it twice, which I guess means is that like both the value and like the state are equal, which I guess makes sense because yeah, we want to like read out the state, so we sort of need to copy it to the second position in the tuple, which is like the result, I guess, that will be passed to the next like function that we're gonna see in our and then definition later probably. Yeah, and now we have to also define a set function which will take a value of type sigma and return a state of sigma and unit, which is to say that, well, the state will be of type sigma and there's no result or like only a trivial result. So yeah, the value of that will be a function that that ignores its argument and just always sets the state to sigma, or sorry, to s. Okay, so now finally we define our and then function, which will take a first argument of type state of sigma and alpha, and a next function which will take our alpha and return a new state with sigma and beta. So the type of the state stays the same, but the type of the result can change. And obviously the result will just be state of sigma and beta. And the result will be a function that takes a state s, which is of type sigma, and will apply essentially our first action, which or first state, but state is really a function, so I guess it's better to think of it as an action, and pass it the original state. Then we get a new state s prime and a return value x, and then we give x to the next function, and the next function, I guess, returns a state value, but again, a state value is really a function. So to, like, this is left associative, right? So you can imagine parentheses here. So to the result of the next function, we then give the modified state, so that in the end, we are essentially here, we get a tuple. And now we define our squiggly arrow again as an alias essentially for the and then function. And then we can see how we can use this state monad or state type to simulate a mutable local state. So we define the same number function as above, except that now our helper, instead of returning a tuple, returns a state with a natural number as the state and a binary tree as the result. So again, the first thing will be to call it on the left subtree. Then this will return in a state value, which is passed to our and then function as the first argument. The next will then be a function that takes the actual return value from that, which we name as numbered left. And here's where it gets interesting. So we use this get action to get the current value of our like pseudo mutable variable, and we call it n, and then we set it to n plus 1, which doesn't give a result, so we have this lambda expression with unit type pattern here, and then we call it on the right subtree. And I mean, yeah, it's pretty similar to the original function, but what we don't have to do anymore is like manually manage that state. We can just use this get and set, which under the hood will do the same thing that we did essentially earlier. Yeah, and I mean, if you're wondering why get and set like don't take variable name, I mean, the way we implemented state is it supports literally only one single variable, so we don't need to give it a name or anything. Get will just get the single variable and set will set it. 4.1.5 monads, a functional design pattern. So in each of the examples that we saw, we had 4 things. A polymorphic type, for example, option, accept, with log or state. And I guess what's also important here is that we have a polymorphic type with only one, polymorphic type that's parameterized by only like one thing. So in the case of option, it's just option itself. But in the case of accept, we have to like fix the first parameter. That's why in option we don't write option alpha here, I guess, but in accept we write accept epsilon because accept actually takes two types as arguments. And yeah, the same for with log alpha and state sigma. And an operator and then that will take care of the repetitive aspect of sequencing the programs that have this type. An operator OK that is how they describe it here, the most boring way to use the type. So in the option case, it would be just setting, like returning a sum value, or in the state case would just be like keeping the state as it is and just setting the return value and so on. And the fourth thing is something that will be then different for each concrete like monad, because like for the accept case we have this fail function, for the log case we had this save function, for the state case we had this get function. And obviously it doesn't make sense to like, this is then specific to one particular monad, like the state monad. The get function then cannot be used with like the option monad, for example. And yeah, I mean, spoiler alert, this type of API is called monad. Yeah, so really there somehow is this big scare about monads because it comes from like mathematics and from category theory. But I mean, that's just the name. You could have called it anything. So it's really just a type class, or like a design pattern for a type of API that you often see not just in functional programming languages but in all programming languages. And I mean, one way to think about monads is that each monad encodes a particular kind of side effect, but it encodes it using like a purely functional values and functions. So option represents a program that can fail. Accept represents a program that can throw exceptions. With log represents a program that accumulates a log. And state represents a program that has a mutable variable. 4.2, the monad type class. Rather than having to import an operator like OK or and then for each type that is a monad, obviously in Lean we will have this in the standard library and have it as a type class, so we don't have to define our own names. We can just overload the type class for our type. And this will allow us to use the same syntax and operators for all instances of monads. So in the monad type class, there will be a pure function, which is like the OK function that we had in the previous section, and a bind function, which is like the and then function that we had. And what we can see here is that we have this m, which is a function from type to type, which is to say that it is a polymorphic type that's parameterized in one type. And obviously the pure function is then going to take just a value of a type alpha and return a monad value of type alpha. And the bind function takes a monadic value of type alpha, then applies a function to it that takes alpha and returns another monadic value of type beta. And yeah, and the end result is just then the result of calling that function. So m of beta. Yeah, so this is a slight simplification, and later we will see the true definition, but that's the gist of it. So now we can define an instance of monad for option, where pure is just sum and bind is just a pattern match, which will propagate the non-value and call our next function on the sum value if the option is sum. And in case of the accept, again, accept takes two types, so we have to like fix one of them, which is this epsilon, and the second one, which is like the OK type, will be like the type in which the monad is parameterized essentially. And obviously pure will just be accept.ok, and bind will be a match expression that checks for an error and propagates the error. Or in case there's an OK value, we continue with our computation and pass it to the next part. So now we can generalize our first, third, fifth, seventh function for any monad. And since there might be different ways to look up the value, we now need to pass like this lookup parameter. And we are using this operator, which is conventionally the infix operator for the bind operation in the monad. So it's also used in the same way in other programming languages, like in Haskell, and plays the same role as the squiggly arrow that we had in the previous chapter. And I kind of forgot what the square bracket syntax meant. So I guess it's some kind of syntax to denote a type class constraint like this, but I don't really remember from the previous chapters where that was explained. But okay, so basically we're saying that m needs to be implement the type class monad. So we look up 0 and then, well, we get the first, look up 2, we get the third, and so on. And then in the end, we just return with our pure function this tuple. And now obviously we can use it, for example, with just the option monad. And obviously we can also use it with the except monad if we define the appropriate lookup function. 4.2.1 General monad operations. Yeah, and now because we have this abstraction over all these APIs, if we can define functions that work for all monads, then those functions will obviously be very generic and very powerful because can be applied in a lot of contexts. So for example, we can define a monadic version of the map function. So we have this mapm function, which requires that lowercase m is a monad, takes a function f from alpha to m of beta and a list of alphas, and returns a monad instance, or like an instance of the monad m type list of beta. And obviously in the empty list case we cannot really do anything, and if the list is non-empty, then we apply our function x and bind the result to hd, and then we call the function recursively on the axis, on the tail of the list, and bind the result to TL, and we return a monadic value with the head prepended to the tail. And well, obviously this now works for any monad, so we can use it for functions that produce logs, for functions that can fail, for functions that use mutable state, and so on. Yeah, so again, if we want to define an instance of monad for state, which was a type that's parameterized by two other types, we need to fix one of those types. So in this case we have the sigma, which is the type of the state itself, and we leave the type of the result like polymorphic, and we can define an instance monad for state sigma by defining pure to be a function that just takes a state and leaves it unmodified but sets the result to x, and bind to be function that takes a first action, so first state essentially, but again state is like an action, and a next, which takes the return value, the first action, and returns another action. And yeah, so we take the initial state, we pass it to the first action, and yeah, then we pass the result to the next action. Yeah, so this obviously introduces the constraint that the type of state cannot change during a bind. So state has one fixed type, sigma, but the type of the result can obviously change. Now we can, for example, define an increment function, or an increment action rather, that is of type state int. And the first thing we do is call the get action to get the current value, and then call the set action to increment it by the how much parameter. And if we pass increment to mapm, then we would get a function that computes the sum of the entries in a list. So the mutable variable in that case would contain the sum so far, and the resulting list would contain a running sum. So if we then look at the type of mapm increment, the type would be list of integers to state of integer and list of integer. And if we expand the definition of state, we get list of int to int to a tuple of int and list of int. So this here would then be essentially the initial sum, so we would have to apply a 0 here. And again, the result, yeah, in the example would be here the total sum and a list of the running sums. Yeah, and for the logging monad instance, we have this type logged, which the instance is polymorphic over, so it will work for any type here, but the bind function cannot change the type of the logged data. It can just change the type of the second argument of this with log type constructor. So again, in the pure case, we leave the log as an empty list and just set the value. And in the bind case, need to like append the two logs of the result and the next action, and the value is just replaced by the result of the next function. So now, for example, we can define a function save if even, which will log even numbers but leave the argument unchanged. So get an argument I, and we return a with log of int and int. And if I is even, then we save it to the log. Otherwise, we just call pure, which leaves the log unchanged. And in the end, we overwrite the value to just be I. So if we call map variable, if we map this save if even function over a list of numbers, the log will contain the even numbers and the value will just be the original list. 4.2.2, the identity monad. Yeah, so now since we have this monad type class, we can write these sort of functions that work with any monad, so any kind of side effect. And maybe some of these functions are so useful that we want to use them even when we are not working with monads. So there's this thing called an identity monad, which is just like a trivial monad that has no effects, but it allows us to use pure code in monadic APIs. So we have this type constructor ID, which takes a type and returns a type, and it's just the type itself. So I guess it's like kind of a wrapper type. And we can define a monad instance where pure x is just x and bind xf is just function application. Yeah, so the type of pure is really alpha to ID of alpha, but ID of alpha obviously is just alpha, so we can return x without like having to actually wrap it in anything. And the same for the type of bind, so it would normally be alpha to a function that takes an alpha and returns an ID of beta, and the end result would be an ID of beta. But because of how ID is defined, this is just alpha to a function from alpha to beta, which, I mean, the only way to basically implement something like that is to just apply the function. Yeah, now we can use our map m function as a regular map function, and apparently it cannot like deduce the type, so we have to specifically like set the value of this type constraint here of this m in this constraint to be ID, and then we can pass just like an increment function and a list, and it will increment each element in the list. Yeah, so if we leave out the type of the monad, then we will just get a scary error message. 4.2.3, the monad contract. And obviously, I mean, if you have the type class, like for example, in the case of Boolean equality and hashable, you should ensure that the two equal values hash to the same thing. And in a similar way for monad, there are just some rules that you should follow when implementing the monad type class. And one of those rules is that pure needs to be a left identity of bind, which is to say that bind of pure of v and f as a second argument should just be the same as f of v. I mean, which makes sense, like bind is just applying our action to the result of the previous computation, and if that result is v, then it's the same as like literally applying the rest of the computation, or like passing v to the rest of the computation. And also pure should be a right identity of bind. So if we do bind of v and pure, then that's just v, because bind again takes the previous result and passes it to the rest of the computation, and the rest of the computation then just says, okay, essentially return v. So yeah, then obviously it's just going to be v, or if you don't define it in that such a way that that's true, then like a lot of stuff is just not going to work as expected. And also bind should be associative. So if we first run v and pass that to f and pass the result of that to g using bind, that should be the same as basically, yeah, running v, passing the result via bind to this lambda, which will then first evaluate f and pass the result to g. Honestly, think this is an instance where it might be better to use the operator instead of like the name. So I'm just looking it up like for Haskell, and they have a formulation where they use the operator, and here you can just see that, I mean, we have to introduce this lambda here, but essentially what we're just doing is moving the parentheses around. So here the parentheses are on the like left sub-expression, and here they're on the right sub-expression, and that's just, yeah, what associativity is, just to say that it doesn't matter which one we do first, the left part or the right part. Yeah, so they have also here a more intuitive way of seeing it, so that pure should have no like side effects, and if it doesn't have side effects, it yeah, it doesn't matter. Like if we sequence it with bind, it's just going to be an identity. And the associative property of bind is essentially just saying that the sequencing bookkeeping doesn't matter for the result as long as we keep the order of the actual actions the same. Exercises. Okay, so we should define a map function over a monad. Sorry, we should define a map function over a binary tree that does a pre-order traversal. So I guess that means first the current data point, then the left subtree, then the right subtree. Let's copy the definition from the previous chapter and also our previous map function that we had. I guess this is, but in this chapter they are using a different bin tree. Let's go to definition. No, it's the same. Let's see if the AI is correct. So obviously we need to pattern match, and in the leaf case, obviously we just need to, no, that's not pretty sure we should be calling our function. Oh no, the leaves in this binary tree don't have any data. Okay, yeah, so I guess let's delete this, say left, right, and trying to use do notation here, which we haven't even introduced yet. So if we say we are going to do in order, then we're going to have to do apply to the x, no, pre-order. Pre-order, we have to apply it to x first, so we apply f to x. No, we have to use here this syntax. And for left and right we do a recursive call, and as the result we just return our modified left and right branches, but that seems to not work. Okay, because we have this monadic value here, so we need to obviously bind it like this, and the same with the right one, and also the same with x. Sorry, yeah. I think probably later in the chapter we will see that we can write this much nicer using do notation, but yeah, pretty confident this is correct. Okay, the next exercise is about the monad instance for option, which was this, and we should think about why it satisfies the monad contract, where the contract was basically this. So let's see, well, some x bound to bind k should just be like, no, sorry, pure of a bind k should just be like ka. Well, pure a is really just some a and some a applied to k according to this match where k is next, so it's just ka. So yeah, pretty clear. Some a applied to k is just ka. Let's see, the other rule was about the right identity, so I guess here we have to think about both cases, but obviously none to pure is just going to be none, and with the sum case, if you give sum to pure, then we will just literally produce the same value. Just will be passed to next here, and then we will go to pure and return, like we unpack it and then we repack it essentially into the sum, into the option. And for the associativity, it's going to be maybe a bit more annoying to show that. So, I mean, maybe annoying to write it down, but if you think about it, like the none gets just always passed through. So if we like give a none here, it's just going to return ignore this part of the computation and give us a none. In this case here, it's going to like ignore this part and just give us a none, and then this whole thing is going to be none, and then the whole expression is also going to be none. And in the sum case, let's say sum x applied to this whole thing will just give us kx bind h. See the other direction. If we take some x and bind it to k, and then bind the result to h, so basically this part, then obviously we will get kx bind h, which is the same that we got here. So yeah, we can conclude, I think, that the laws apply. And for this wrong instance, well, obviously it's not going to have the identity property. So if we do this, then obviously according to the laws we should just get some 42, but with this kind of instance we get none. So that's where the wrong instance violates the law. Yeah, with the correct instance, we can see we get sum 42. 4.3 example, arithmetic in monads. So I guess on the one hand, you can view monads as this sort of like walk around that we have to do in functional programming because we don't have side effects. But on the other hand, using monads also like provides benefits. And the first one is obviously that now we have to be honest about side effects. We cannot like hide them. We have to declare them in a type. And yeah, we don't have to look at the implementation anymore. If we see the type signature, yeah, we then see what side effects this function can do. And it gives you a kind of flexibility. So in a normal programming language, usually there's some monads will be built into the language, like exception handling, for example, or like async await, for example, or like this null coalescing or null threading. But if you have this sort of general monad abstraction in your language, and obviously you can define like arbitrary monads, and you can decide which ones you want to use and which ones you don't want to use. And in this example, we're going to look at an evaluator for arithmetic expressions. 4.3.1 arithmetic expressions. So we're going to consider arithmetic expressions to be either literal integers or binary operator applied to two expressions. So we define an inductive expression type with our operator type, and we have a const, which is literally just an integer, and a primitive operation, which takes an operator and I guess a left expression and a right expression, and then returns a resulting expression. And we have plus, minus, times, and division as our operators. I don't know why they make it so general here, so you could just say that OP is of type arithmetic operator. Instead, they let us give an arbitrary type here. So if we want to represent 2 plus 3, then yeah, we have the plus operation with constants 2 and 3. And obviously we can also do arbitrary complex expressions. 4.3.2 evaluating expressions. So obviously division by 0 can fail, so we need a way to evaluate an expression given that it can fail. So we can use the option type, and here we can use like the option monad. First evaluate the left sub-expression, then the right sub-expression, and if they're both not none, then we check which operator we have. And yeah, in all cases except division, we just evaluate it, and if it's a division, then we need to check for 0, and in that case return none, otherwise just perform the division. So this function mixes two concerns, evaluating the sub-expression and applying a binary operator to the results. We can split it in two parts and apply a primitive that just takes an arithmetic operation and two integers and applies the operation, and an evaluate option function that takes an arithmetic expression and returns an optional integer. Yeah, where now we just call the second function, the helper function. And again, yeah, we are now using this monad. So like what we're doing with the option monad is we just always return none if the expression is invalid, but maybe we would want like an error message. So we can like modify the code to use the except monad instead. And it's pretty much the same code, except for returning none here. We give a useful error message, and the evaluate except actually is literally the same code. And obviously now, since this is basically the same, we can like generalize it and just pass the application function as an argument. So we have here one for the option case, one for the exception case, and we have our evaluate m function, which takes a monad m and an apply prim function that goes from an arithmetic operator, an integer and another integer, to a monadic integer. And given those two things, we can construct a function that goes from an arithmetic expression to monadic integer, which is literally the same function that we had above already. And now we can call it with the option application function and with the exception application function, and we get the correct return value. And since division was the only real difference, I guess we can refactor it further to just change the division part and make the apply primitive also generic over the monad, but obviously for the division we need to pass it in as an argument now, or as a callback. And yeah, I mean pretty much the same as before, except now instead of apply prim, we're passing apply diff to the evaluate m function. Yeah, so now it's very clear how the two code paths differ, and that literally just the handling of this one error case is the difference. 4.3.3 further effects. So I guess now we extend our type of primitive operations to still have plus, minus, and times, but now it also has this case other that takes an instance of a type called special and returns then a primitive operation parameterized by special. So special is, I guess special is a type, and other is a function that takes a value of special and gives us a value of prim parameterized by that value of special. Yeah. Okay, now we have our another inductive data type that just has one case, which is the division. Don't yet see where this is going, but the second step is to broaden the scope of the division handler argument to evaluate m so that it can process any special operator. So now we have diff option as a function that takes a can fail value, which is just going to be division, and then takes two integers and then returns an option of integer. And obviously, yeah, we can pattern match on it, but there's only one possibility. And we can define the same for the exception case. And now in apply prim, we have parameterized it over this apply special function that will apply the other operators. Yeah, and we have to do the same modification to the evaluate m function. So I guess this now helps us to maybe easier be able to extend them more easily, so we can add other operations that can fail, I guess. 4.3.3.1, no effects. Yeah, so Lean has this type empty, which has no constructors, so there can never be a value in that type. So yeah, it's like the empty set basically. And we can use that to indicate that a function cannot be called. So maybe it's a little bit different like in other languages where you have a nothing type or like a never type like in Rust that just indicates that a function will possibly like run forever or crash the program, but I guess in Lean just indicates that the function cannot be called. Yeah, and there's also this special syntax for it then called no match, which tells Lean that yeah, we don't need to give a value because this expression can never even be called. Okay, so now we could use this empty type for our prim.other constructor, and that just makes it so that now we can no longer fail, I guess, because well, empty can never be constructed. So we have an apply empty, which takes a monad m, an operation of type empty, and two integers that are ignored, and ostensibly gives us a monadic integer, but really we're just calling no match on the operator to sort of prove that this can never be called. So if we now use the identity monad and our apply empty, then we can evaluate a function without division, and the resulting value will no longer be an option. It will literally just be that value. 4.3.3.2 non-deterministic search. Yeah, so another way to handle failure instead of like aborting the program could be to backtrack and just try a different input. And yeah, I guess now we're going to extend our evaluate m for that case. So now in the evaluator we have to not just return a single value but a multi-set of values. So constant n is just going to give us the set n, plus operator is going to give us all the possible combinations of its argument added. And the same for division, except that we exclude the case where the divisor, or like the second argument to the division, is 0. And we also have this choose operation now that will allow us to introduce two possibilities. So for example, if we then have 90 divided by choose minus 5 or 5 plus 5, obviously we cannot choose minus 5 because then we divide by 0, but we can choose 5, so then we divide by 10 and we get 9 as a result. And the reason we're using multi-sets here is just so that we don't have to check for the uniqueness. So I guess in the end we can just use lists then. So now we can define our inductive type for our monad, which is called many, and is parameterized over a type alpha. There's a none constructor and a more constructor, and more will just be like a function from alpha to a function that takes an alpha and a producer of alphas, I guess, and then it returns many of alpha. So I guess this is like kind of analogous to a list. So you have the empty list and you have your cons constructor, right? Where you have a head and a tail. Now we can define a one constructor that will just, well, take our one value and as the rest just give no values. So yeah, I guess really just is like a lazy list basically. So in Haskell or in a lazy language, I guess this would literally like just be like a list, but since Lean is strict, we have to do this sort of deferred evaluation here, like pass this thunk that can give us a value of many alpha. Okay, and now we can also create a union of two manys, which I'm guessing will just be like prepending to a list. Yeah, so just we get the head of the first element if it's not empty, and then as the second element, or like as the tail, we call ourselves recursively. And I guess the reason, yeah, we have to pass this unit type here is that this is like the callback or the thunk that produces the access. So yeah, basically at this point we're just like simulating lazy evaluation, and we can define a function that converts a list alpha to a many alpha, literally just by like wrapping the tail of the list into a callback or a lambda expression. Yeah, so now we're just like redefining a bunch of list functions like take or take all. But take all will I guess then just be like the conversion back to a list, and take will just be like taking a specific number of elements and just not evaluating the rest. So if we now define like a bind function for our many type, it will take a many of alpha and then a function that takes alpha to many of beta, and the result will be a many of beta. And if our first argument is none, return none. If there are more x's, then where we take the first and we take our function, we apply a function to the first one, and we union that with, well, applying it to the rest of the x's. And since that union function was defined lazily, if the first one like meets some criteria, like we can sort of stop the evaluation, I guess. So now we can check the monad laws, I guess. So check that many.one and with many.bind gives like an identity function, which we can see seems to be true. So in the end we just apply, or if you have many.bind of many.one v and the function f, then in the end we literally just got f.v and as a union with the empty set. And so for the second law, if v has the form of like a set of n possible values, then many.bind v with many.one will give us the union of like applying many.one to each of them, but the union of like each of these individually is just like the same set again as in the beginning. And okay, now we also need to check the associativity. So we need to check that many.bind of v and f, and then g as a second argument is the same as many.bind of v and then a lambda function that takes an x and returns many.bind of f of x and of g. So many.bind of v and f will just be the union of applying f to all the possible values of v, which means if we bind that to g, then it will be like binding the first one to g union with the second, third, and so on. And I guess for the other case we arrive at the same result. I mean, this is kind of like technical and not very exciting, I guess. But so we can prove that many.bind is associative. So if we define our monad instance, we just use many.one for pure and many.bind for bind. And using this monad, then we can, for example, define a function adds2 that takes a goal, which is a natural number, and a list of natural numbers, and we can find all combinations that add up to our goal number. So if the list is empty, then we check if the goal is 0. Then if yes, we can just return the empty list. So there's like one combination of the empty list that adds to 0, which is the empty list. So if we add nothing, then we have 0, I guess. And if the goal is not 0, then there's no way to do it. And if you have at least one number, then we check if x is bigger than the goal. If it's bigger, then well, it cannot be included in any sum. Well, because we have natural numbers, so no negative numbers. So we just call adds2 on the tail. Otherwise, we call adds2 on the tail and union that with, let's see, like taking the goal minus x and finding all the ways to produce goal minus x for the tail. And for each of these answers, then we add x to the answer. Yeah, I mean, if we find all the ways to produce goal minus x and then we add x to the answer, then we have found all the ways to produce goal minus x plus x, which is just the goal. Yeah, now we make a helper function print list to like print one list per line so that we can visualize the result. And yeah, we have this list of numbers from 1 to 10, and we find all the ways to add up to 15, which is actually quite a lot of ways. But yeah, I mean, this sort of program, I mean, without using this non-determinism approach, you would have to do like a lot of bookkeeping. I mean, this is still a simpler case, but like if you have a more complex case, so I think it can be really useful to have that. But obviously also it gets harder to sort of like intuitively think about the running time, because almost, well, I mean, if you have this sort of non-determinism, you often like get, yeah, really bad running times if you end up searching all combinations of all possibilities. So if we have if we define an inductive type needs search to be either diff or choose, then we can make a function needs search that takes a value of type needs search and 2 integers and returns a value of many of integer. And I mean, for choose we just have those 2 values, and in case of the division, well, either we get nothing or we get 1 value, which is the result of the division. And yeah, now we can use it with our evaluate m function and get a list of like possibilities back, or in case there's like a division by 0, just get an empty list. 4.3.3.3 custom environments. So we could make our evaluator extensible by allowing the user to define arbitrary operators, but then obviously we need some sort of environment, like for example a hash map from string to function that implements the operator, that we then will need to pass down each recursive call. And that's also just like some bookkeeping that we would like to avoid. So there you can use the monad pattern to like abstract that. That's then called a reader monad. So we need to change then the rules of our evaluator. So a constant will evaluate to a lambda expression that ignores its environment and just returns the constant. Arithmetic operators need to pass on the environment. So if you have f plus g, we need to pass the environment to f and to g. And for custom operation, we need to check if the environment contains the operation. And I guess we just use 0 as a fallback here instead of like doing any error handling. So for this monad, first we define our reader type, which takes a type row and a type alpha, and returns another type that's just then a function from row to alpha. So like literally similar to our state monad, except that now the state is like read only. Then we define a function read, which is a reader of like row and row, so like get in the state monad, where we just take the state and also return it as the value. Yeah, so for pure we can just ignore the environment, and bind will be a bit trickier. So the type of bind would be reader of row and alpha as the first argument. Second argument would be a function alpha to reader of row and beta, and the result needs to be a reader of row and beta. And let's just try to unfold the definition of reader. So then we have as the first argument a function from row to alpha, as the second argument a function from alpha to row to beta, and the result is just row to beta. So we can see that yeah, I mean, that makes it a bit clearer how it should be implemented. Okay, so now they're saying we can get help from Lean with this function. I mean, let's try. Not from Copilot, thank you very much. So we are defining a function here which has 3 types that be inferred. I think that was the implicit binder. Yeah, regular applications whenever all. Yeah, implicit parameter that's determined from the other arguments. Yeah, so I guess we can like go through like and at each step look at what error message we get. So here we get that we are expecting a function from row to beta. So I guess the first step is to make a function env. Let's keep it at that. Then we see, okay, now what we want is a beta, and the only way to get the beta is from next. So we have a row, we have a way to go from row to alpha, and we have a way to go from alpha and row to beta, right? So we need to call next with, yeah, like this basically. It should work. Yeah, and this is also what they're doing in the text here, just going through and making these like placeholders and checking like the expected type for each of the placeholders. And we arrive at the definition. I'm not exactly sure why we had to pass like define these implicit parameters, and here we leave them out. I think it was just to get a better error message in the end. Yeah, so that approach is just called following the types. So obviously if you're just like looking at the types and trying to get the right thing, I mean, sometimes it works, but sometimes then you end up not understanding the program. What, as far as I know, like if you use Lean as a proof assistant, that's basically how it works. Like at each step you see like which type is expected and you need to like construct that. And the cool thing in the case of a proof is like you don't even need to understand it in the end. As long as you find something that works, then you have proved your claim, and Lean will check that it's correct. But obviously in case of a normal program, just because it has the correct type, that doesn't mean it will like necessarily do what you want. Yeah, so they're saying you can just write something by following the types and then try to unpack it later to find out the meaning of like what you actually even wrote. So now we're checking that reader.bind obeys the monad contract. And I mean, I don't think we need to go through all these proofs. It's just kind of like technical, just like substituting the definitions in there to see that, well, it does indeed do the correct thing in the end. Yeah, so I'm also gonna skip the proof for the associativity here. Now that we have proved the monad laws, we can just define, yeah, our instance. One thing that I'm actually wondering is, since, I mean, Lean is like a proof assistant, right? So maybe there's a way to like explicitly supply a proof for the monad laws in the language itself, rather than just like writing it in a document like this. Yeah, maybe it will come up later in the chapter, I don't know. So we're going to use just a list of pairs for our environment, where the first element is the name and the second element is the function to compute it. So for example, you can add a max operator and a mod operator, and then we can use list.lookup to do like a linear search in the list to find the operator, and have our, yeah, use that to define a function apply prim reader that takes an arbitrary operator and results in a reader that has an environment and an integer as a result. Yeah, and I mean, in other languages you would like usually define some ad hoc way to do this, like a context parameter or like a dynamic variable in Lisp. But yeah, since in Lean we have this monad type class, we get sort of this nice language, and as we later will see, also syntax for, yeah, for this reader effect and also all other effects. So exercises. I think I'm gonna skip this one about checking the contract. That's usually just like substituting the definitions and doing some transformation. Readers with failure. Okay, let's see. Reader option takes the type row and type alpha, and the result is like a reader but now optional. Let's see, for the pure case, well, we need to combine like the pure of the reader and the pure of the option, I guess. So we just have a function that ignores the environment, and essentially now it does option.pure, which is like sum. Then for bind, let's see. the type is that we have a result and the next function, and we want to give a reader option in the end, so we have functional text environment. We need to match the result. What I'm wondering is if we can actually call the option monad inside of here. So if we just do it like this, yeah, then we can avoid some of the boilerplate, I guess. But yeah, I mean, that's also like about how far I got with Haskell, because I mean, monads are like really nice as long as you only have one of them, but it gets a bit more trickier when you need to like combine different effects. And like I think Haskell does this like with monad transformers. I mean, probably Lean also has some like abstract way to do it, because essentially, I mean, this is just like boilerplate, like we're defining a combination of two monads, but what if we want like now also like a state, then we have reader option state, and we have to like create an exponential number of like types to deal with all the possible like combinations of effects. So I'm sure they have some like abstraction for that. And I mean, for except it's going to be similar, right? It's crazy how good actually Copilot is. For some reason that this wouldn't have expected it to like be able to like then directly come up with the correct type signature. Let's see if it was actually correct for the reader option. Well, it doesn't complain here, at least. For the bind, actually should be the same. We should be able to then now use the except monad inside of here. So just call the bind of the except monad. Yeah. Not gonna try it out, but pretty sure that it's correct since the types all line up. Yeah, so if we define apply special reader except with a reader except type, I wonder if they have the code somewhere. Kind of hard to copy paste all the required definitions. So I guess we also need a read except, and then here we can do, why can we not do that? No, okay, we have to give a reader except result. I guess we have to have a fail, and then if we do fail like this, and okay, we get 9. If I use some invalid, we get our exception. Yeah, so it works, but we have a lot of boilerplate at this point. Okay, a tracing evaluator. Okay, I'm having a hard time even understanding the exercise, but okay. So we have this type class to trace. Sorry, we have this inductive type to trace. So the first part is easy. We should take our with log and make a monad instance with just the functions that we had before. Okay, so obviously you have to save, and then, so we're saving it to the log. Okay, but apply prim, what was the type of that? Apply prim had function, takes a function which takes some special thing, and I wanted to use this no match thing to say fun, to say that, well, the special thing in this case is empty, so can never be applied. And yeah, well, we actually apply our operation, right? Let's see if it does what it's supposed to do. Oh, we were not done yet. Wait, it's not giving any error here, right? So why can I not do open? Why is it not giving me an error when I comment it out, but then it says unexpected token, unexpected end of input? Okay, apply prim text apply special function, which we are supplying. Then our operation, which is of type prim empty, and then two integers, and then it gives us, it just calls pure for us, essentially in this monad. Can we assign m explicitly? That does not help. I'm using the wrong syntax for a function, for lambda expression. Yeah, maybe we have one argument too many. Okay, so this works, but I would really like to avoid having to do definition for something that's never going to be called. Okay, so now it should work, right? No, apparently not. I don't know why it's trying to adapt something to IO. Let's just type with log. Yeah, cannot evaluate it. Okay, now we can somehow print it. 1, 2, 3, 4, 3 minus 1. 1, 2, 3, 3 minus 1. Yeah, but yeah, so the issue was the missing wrapper instance. But the error message was really confusing, so I don't know what's up with that. Ah, okay, it's literally written here. Could have read the whole exercise. Okay, well, anyway, yeah, so it kind of looks noisy if we have to keep using this infix bind operator, and that's why there's some syntactic sugar for it. We already saw it actually in the Hello World chapter with this do keyword, and I guess now we're gonna see how essentially do is just translated to a monad or like a monadic expression using this like bind operator. So if you have a single expression, it just does nothing. If we have a let binding and a bunch of statements, then that turns into a call to the bind operator. Like the let binding is literally like a lambda that gets passed to the bind operator to like bind the result to the parameter of the lambda. And when we are not using a let, but we have like a monadic value here, then that just means we are ignoring the result essentially. And like as a convenience, we can also like just use a normal let inside of monads, which then just gets like moved outside basically, or like which just gets ignored by the do syntax. So now we can rewrite this noisy function that we had previously using the much nicer do notation with this like let notation with the arrow to bind the results of our monadic actions. Same for the function to number our binary tree. Yeah, it just looks that much nicer. And I mean, one thing that you can notice is especially here with the state monad, it now essentially looks like an imperative program. I think that's also why monads are sometimes called like programmable semicolons, because this do notation and the monad type class essentially allows you to customize like the behavior, what happens after the end of the line, like what is like the semicolon doing essentially, like so to speak. Can also rewrite our map m function with the do notation. Yeah. And I mean, Lean has this feature called nested actions, so we don't need to explicitly type it, bind it to a name. We can just like inline it here, and then it basically looks like a normal map function. And then we can make the number function like really concise. So, yeah, literally using the nested action here instead of having these names. So now it just looks like a normal like recursive function basically, except for these arrows. Okay, let's try to just rewrite evaluate m using do notation. Where is it? And for some reason with Lean, VS Code gets really slow at some point, so restart it. Let's make it here, and we can do this by using these nested expressions in the do notation, making it a lot nicer to read and a lot shorter, I guess. Okay, and this one is already using do notation, but we can rewrite it using the nested expression. So literally just is a single line now. Yeah. The IO monad. Okay, I mean, we already had like a section on the IO monad earlier, this like running a program in chapter 2. And one perspective how you can interpret it is that an IO action is like an instruction to the runtime system of Lean to essentially execute a side effect. So like, for example, read a string from a file and then invoke some pure Lean code on with this string. Yeah, so this is like an exterior perspective that views the program from the perspective of the operating system. So in this perspective, pure is just an IO action that doesn't have any side effects, and bind, well, takes one action that does a potentially effectful operation and then continues on with the rest of the program. And the second perspective is that an IO action like transforms the whole world. And from that perspective, an IO action is actually like pure, like everything else in Lean, because they just get a unique world as an input and then return the changed world as an output. And this is like the interior perspective. Like this is how like semantically IO works inside of Lean. But I mean, obviously you cannot like implement it like that. You cannot like take the whole world as an argument. So the way like you implement that is that you represent the world as sort of a token, and then you can structure your code of the IO monad such that that token is used exactly once, But I mean, especially in the case of I/O, personally, I just think it's probably easiest to think of I/O values as actions. Yeah. Yeah, so we know in Lean that we can use this hashtag print syntax to see how something is defined. Like for example, natural numbers are an inductive data type with like two constructors, right? Or char.isAlpha is like a function. So, or if we print list.isEmpty, then we get something that uses some syntax that we haven't seen so far, like this dot curly brace u. But yeah, that apparently we can ignore for now. But let's try printing IO. So we get a weird syntax at reducible def IO type to type EIO IO.error. Yeah, so IO is just defined as error IO, I guess, or like exception IO. So if we look into IO.error, we can see, well, there's lots of like errors. I guess that mostly is stuff that can come from the operating system, like that something already exists, or that resource is busy, or that the hardware is faulty. Yeah, and this EIO of epsilon and alpha is just an IO action that will either give you an alpha or give you an error. So pretty much like the accept type. And let's see how EIO is defined. It's just a function from type to type So it takes two types and gives a type. And let's see, takes a type epsilon, then gives e state m of epsilon and IO dot real world. Yeah, so e state m is a combination of accept and state, which looks really confusing, to be honest. But yeah, basically we accept initial state of type sigma, and then we return a e state m result, which can contain an error epsilon, another state sigma, and well, our value alpha, which has a okay and an error case that works like analogously to accept, except that it has an additional state field. So we have like a combination again of accept and state. So for pure, it just returns an okay. Protected here apparently has a very different meaning than in most other programming languages, and just means that I guess we have to always fully specify the name. And for bind, well, we take an initial state and pass that to the first action, and then checks for errors. And if there's an error, we just leave the state unchanged. And if the result was a success, then we continue the computation with the value and the resulting state. And for the state, we use this type that represents the real world called IO.realWorld. And each IO action receives a real world and returns another one. And obviously IO.pure is gonna return the world unchanged, while bind can literally change the world. And obviously this world is just like a token to represent the state of the world. And the implementation needs to make sure that these tokens can never be reused. And if you're making sure of that, then we can literally just define it as a unit. I mean, probably behind the scenes there's a lot more going on, but anyway. 4.6 additional conveniences. 4.6.1 shared argument types. Pretty sure we actually already probably saw this at some point somewhere, but if you have two arguments of the same type, you can like define them like that you don't have to repeat the type. 4.6.2 leading dot notation. Okay, so we can leave out the namespace for constructors in some cases, like for example in this function that works on binary trees, we can just, instead of writing binary tree.leaf, we can just write .leaf, and it will infer that we're talking about the leaf function in the binary tree namespace. Obviously can be used for anything in that namespace, also just like a random function that we define here, like .empty. 4.6.3 or patterns. So we have a function weekday that returns for Saturday and Sunday true and otherwise false. We can simplify it using this constructor dot notation, but we can simplify it even further by putting both of those next to each other because they have the same result branch. And obviously we don't have to name the argument, so if we change the definition to essentially move the argument after the colon, then we can just pattern match it on it without explicitly naming it. So now it's a 2-line or like 3-line function instead of originally 5 lines. Yeah. Yeah, so you can even bind variables with this, like in this function here. And under the hood, this will just duplicate the result expression. So it will, yeah, just literally syntactic sugar. It's not like separate semantics or anything. And literally they're not even required to have the same type. So if we have this either type here with natural number and a weekday, we can have the same branch for both of them, even though they are different types. Obviously, in the result expression, you can only refer to variables that are in all the patterns. So x is only in the first one, so obviously the result cannot contain x here. Yeah, you will get an error if you try. And I mean, again, we saw earlier that under the hood it literally just like copy pastes your expression. So sometimes this can lead to some surprising behavior. Yeah, so this is really weird here. So the in L case obviously is going to override this global variable, or like shadow this global variable, and the in R case is gonna access the global variable. So maybe not the most readable code here. Yeah, so in the complicated cases, it's probably better to be more verbose and write code that's easier to read. Okay, 4.7 summary, encoding side effects. So obviously Lean does not have built-in like side effects in the sense that Python does, like exceptions or mutable variables, but we can encode those effects using pure functions and data structures. Like for mutable state, it's just a function from an initial state to a pair of the final state and the result, for example. Yeah, and since each of these effects then is a type, a program that uses those effects also in the type signature will include those types. So we have this advantage that the type signature makes it very clear what kind of effects a program can do. And yeah, one way to see this is that functional programming doesn't mean that we can't use effects. It simply means we have to be honest about which effects we use. Okay, the monad type class. Yeah, we have this monad type class with this sort of contract or these laws that ensure that bind and pure capture these properties of how we intuitively think of effects, that like, yeah, one thing happens before the next thing with bind. Do notation for monads. Yeah, with do notation we can write like monadic programs in a style that looks like a normal imperative language, like Python, for example. And especially in Lean, they also have some other neat features like allowing you to use these nested actions. But behind the scenes, obviously, this is just syntactic sugar. So in the behind the scenes, it's just going to call the bind operator custom monads. Yeah, so Lean gives you the freedom to choose which monads you want to use, and also with the type system you can like enforce that fairly well. I mean, if you were gonna use another programming language like Python, for example, I mean, obviously you could make like a style or like a coding guideline document that says which things you want to use, for example, that you want to avoid exceptions, but like you cannot really enforce that in CI or inside of your program. So just that's something that the explicitness of like monads in Lean gives you, that you can like enforce these sort of decisions, which side effects you want, which side effects you explicitly maybe don't want. The IO monad. Well, for everything that affects the real world, we're going to have to use the IO monad. Obviously, IO is not that like special. It's just one monad among many other monads. The IO monad encodes mainly two things: the state of the real world and exceptions. And yeah, obviously we need exceptions to model failure and recovery, because the IO operations in general can fail. Yeah. Okay, so that's it for this time. Next time we will look at functors, applicative functors, and monads again.